The conversion of unit hydrographs to a different duration uses either superposition or S-curve methods. But how if the conversion involves unit hydrographs, which are not multiples? Check it out here in hydrology. From the previous videos, when we derive a unit hydrograph, note that the examples such as the one presented contain a direct run of hydrograph with 2 hours intervals. Then we have converted this DRH into a unit hydrograph of the same interval, a 2-hour unit hydrograph. So to cut it short, a 2-hour DRH is provided and converted into a 2-hour unit hydrograph, or a 3-hour DRH was converted into a 3-hour UH. But how if what we have is a 3-hour DRH and what we needed is a 2-hour unit hydrograph? Are we just going to work on ratio and proportion? What is the S-curve? The S hydrograph, which is also known as the S-curve, signifies a continuous effective rainfall at a constant rate for an infinite period. It actually looks like the letter S. To illustrate it, we start with the unit hydrograph, where at certain time intervals there are discharge coordinates. We term them right now as U's. These coordinates are used to derive the S-curve, using the cumulative unit hydrograph coordinates. This is like adding U1 to U2. Then, the succeeding coordinate consists of U3 with the accumulated previous coordinates U1 plus U2. The next coordinate adds the cumulative U1, U2, and U3 to U4. For the succeeding point, U5 has the cumulative U1, U2, U3, and U4. So basically, each coordinate takes the cumulative coordinates of the previous. Check that the end of the table creates a constant, as shown in the graph. This is in contrast to the thinking that the values in the table should zero down. Given a 2-hour unit hydrograph for a certain watershed, we are to derive a 3-hour unit hydrograph. The S-curve method requires us to create an S hydrograph, starting with 0 at 0, add 18 to have 18 at T2, then add 40 to get 58 at T4, which would be added to 38 to have 86 at T6, then add 12 again and get 98 at T8. 98 remains constant throughout the end of the curve. The next step is for us to log the S-curve. However, what we need to log are 3-hour S-curve coordinates, which means we need to interpolate the values before placing them in the table. T3 is between 2 and 4, with the following S-curve coordinates. The difference of 58 and 18 is 40, and since we are looking for the mid value, divide this by 2, having 20. Add 20 to 18 and have the S coordinate at T3, which is equal to 38. We do the same for T5. Take the difference between 86 and 58, then divide it by 2 to have 14. Add 14 to 58 to get 72. At T7, 98 minus 86 is 12, then half of 12 is 6. 6 is added to 86 and get 92. The next thing to clarify is where to place the S coordinates. T3 being between 2 and 4, has the coordinate of 38 at T4. For T5 is placed next at T6, and also 92 for T7 is placed at T8. The rest need no interpolation, as the S-curve remains constant at 98. After the lag, take the difference of the two S-curves. T0 has 0, then 18 at T2. Next is 58 minus 38, which is 20 at T4, followed by 86 less 72, or 14 at T6. At T8 is 98 minus 92, which is 6. Then having 98 for both curves, the remaining differences are 0. After the difference, the 3-hour unit hydrograph is then computed. The divisor is 3 from the desired duration over 2 from the given duration, or simply 1.5. The unit hydrograph then starts with 0 at 0. Then 18 over 1.5 is 12 at T2. Next is 20 upon 1.5, or 13.3 at T4. 14 divided by 1.5 is 9.3 at T6. 6 over 1.5 is 4 at T8. The succeeding coordinates are 0. This is the 3-hour unit hydrograph, preserving the time intervals as was given. The placement of the 3-hour S-curve does not matter much, but the values are interpolated using linear interpolation, although the coordinates are plotted on a curve. So the resulting unit hydrograph is an estimate. An alternative approach to this problem is to recreate the 2-hour unit hydrograph to have the required UH as a multiple. We should create a 1-hour unit hydrograph to be able to lag the required 3-hour unit hydrograph. We already have coordinates at T2, 4, 6, and 8. But what do we do to look for the missing entries? To complete the column, we use interpolation. For curves, the interpolation used is the one learned from numerical solutions. We will interpolate using Gregory-Newton forward interpolation. For this method to work, we are required to look for the difference table, since we have equal time intervals. For the first difference, we start with 18 minus 0, or 18. Then 40 minus 18 as 22. Next is 28 minus 40, which is negative 12. And 12 minus 28 is negative 16. Having no constant values at this level, we then take the second difference, starting with 22 less 18, or 4. Next is negative 12 minus 22, or negative 34. And last is negative 16 minus negative 12, which is negative 4. With different values from this level, we then need the third difference, that is negative 34 less 4, giving negative 38. And negative 4 minus negative 34 is 30. Then we have the last difference from 30 minus negative 38, giving 68. Take the leading forward differences, and they are 0, 18, 4, negative 38, and 68. These are the deltas we use for the forward interpolation equation as shown below. With the leading forward differences, we can interpolate at T1. R is 1 minus 0 over 2, which is 0.5. Plug this R into the equation along with the leading forward differences, and UH1 is solved as 3.47. At T3, R is 3 less 0 over 2, or that is 1.5. Plug 1.5 along with the forward differences into the equation and have UH of T3 as 32.47. At T5, R is 5 minus 0 over 2, which is 2.5. Place this into the equation with the forward differences and have UH5 as 37.97. At T7, R becomes 3.5, and place this in the equation to have 15.97. The interpolation using Gregory Newton is basically direct substitution, as long as you can identify the right values. Review interpolation methods in numerical solution in case you have unclear parts of the computation. Going back to the table, the recreated unit hydrograph then is converted into 1 hour unit hydrograph. As we are required to solve for the unit hydrograph using S-curve method, we determine the S-curve for 1 hour. The first entry is 0, then add 3.47 to make 3.47. Add 18 to get 21.47, and again add 32.47 to have 53.94. Next is 40 added to get 93.94. Then 37.97 to have 131.91. Next is 28 to have 159.91. Then add 15.97 to have 175.88. Then add to this 12 to get 187.88. From here, no more entries to add, which places the constant coordinate of 187.88. To have the 3-hour S-curve, the non-zero entries are lagged by 3 hours. So the starting value of 3.47 is placed at T4. Then the rest of the coordinates follow. With the two important S-curve columns already identified, we can take the DRH or their difference. T0 has 0. T1 has 3.47. T2 has 21.47. T3 has 53.94. At T4 is 93.94 minus 3.27 or 90.47. At T5 is 131.91 less 21.47, which is 110.44. At T6 is 159.91 less 53.94, resulting to 105.97. At T7 is 175.88 minus 93.94 or 81.94. At T8 is 187.88 minus 131.91, which is 55.97. At T9 is 187.88 less 159.91, giving 29.97. Then at T10, subtract 175.88 from 187.88, which turns to 12. At T11, the difference is 0. To get the 3-hour unit hydrograph, we divide the difference. The divisor is the desired duration over the given duration. That is 3 over 1, which is 3. From T1, 3.47 over 3 is 1.16. 21.47 upon 3 is 7.16. 53.94 divided by 3 is 17.98. Then at T4, the difference of 90.47 is divided to get 30.16, followed by 110.44 over 3, and that is 36.81. 105.97 divided by 3, which is 35.32. At T6. At T7, 81.94 divided by 3 is 27.31. T8 has 55.97 over 3 or 18.66. At T9, 27.97 upon 3 is 9.32, with 12 over 3 or 4 at T10. This is the 3-hour unit hydrograph using a different time interval from the premise. Try this for your practice. Given a 2-hour unit hydrograph, use S-curve method to derive a 3-hour unit hydrograph. You can try solving using the linear interpolation estimation, where you should have the peak discharge at T12 with 46.7 cumex per centimeter. Then proceed using the higher level interpolation. Good luck!